As I come to terms with how incredible this discovery is that Earth is the ancient star, I have to go all the way back to the very basics of what people need to understand first before we move forward. Asking the really big questions that can wait for now. We have to look at the really simple, basic stuff that we might have missed or forgotten about, if you will. For this talk, I want to go over iron ores quickly. Hematite, which is rust. In its rock form, it's called hematite, but it's just rust. Is 2 irons and 3 oxygens. And with these bonds, you have a double bond here, a single there, and a double there, and a single there. To form those bonds, the rock cycle does not explain how those bonds form. What happened is, earlier during the star's evolution, these elements were separate at one point. They were fully ionized. And that material entered into the star, was ionized, and then recombined, releasing heat as exothermic reactions took place, forming rust, iron oxide. This is magnetite, 3 irons, 4 oxygens. Now the crystalline pattern, I'm not too sure what that is, but you do have a double bond of iron and oxygen on the bottom, and it's the same as the oxide on the top. So you have the double with the iron, single, single, double. And lodestone is what they used to call it, because it led to the discovery of, a compass, or the invention of a compass, I should have said. Because what people did is they found out that some magnetite was magnetic, so they put it on a cork and a pool of water that would remain still, and it would always point north. So maybe they had formed a rock that had like an arrow shape on it, and they would use it to find which way north was. It led to more advanced versions of compass, obviously, because you don't see pilots taking a rock and setting it in the middle of a pool of water when you're flying your plane. That would be pretty bad. Cetera, this is iron carbonate. You have iron, carbon, and 3 oxygen. Notice how the iron is sitting by itself. It's not really bonded. It's just an impurity with that carbonate right there. So you have carbon double bonded to oxygen right there, and single bonded to oxygens up here. And I think this is also suspect for iron coming in after this molecule was formed. So this would have came from outer space in the form of iron meteorites falling down into Earth and then mixing up with this carbonate right here, which is why we also find it, in the surface, and we can mine it out and bore it and chemically alter it and pull all this good stuff out. Limonite, I don't know if I'm saying that right, that also rhymes weird, is hydrogens. Well, look at that. You have water there. Oxygen, single bond of the iron, and then oxygen over here. So this is just a variation of it. I'm sure there are other variations of limonite, but basically what you have here are the 4 main ores to pull iron out, because when you start breaking down these bonds from the oxygens, from the carbons, from the hydrogens, and you get rid of all that excess, you can get the iron out of it. And iron is the main component of steel, wrought iron, and cast iron, and that material is pretty popular these days. Basically, almost everything we use is made out of iron and steel and cast iron and all that stuff. To go a little bit further into this, I want to explain a simple hypothesis, if you will, which I think is beyond the scope of school. So you're not going to learn about this in school. So I suggest everybody pay attention. All right. Remember in an earlier talk where I had Earth as collecting 40,000 tons of space debris, or dust, if you will, every year. Okay? So, outer space material floats around, and as the Earth is going in its orbit around the Sun, it collects all of it, 40,000 tons of it. Now, it's kind of small. It doesn't have a lot of surface area, you know, cosmologically speaking. It's just a little pinpoint, like a little ball on a ballpoint pen just floating around in a giant warehouse. You have Jupiter. Okay? I'm not too sure if that's the scale, but Jupiter, you know, obviously the surface area would be to the power of 2 extra. So Jupiter has a lot more surface area. Okay. Now, when material enters into the star from outer space in the form of comets, asteroids, meteors, I think that's the same as asteroids, just general space debris, okay? Doesn't matter where it came from, doesn't matter what its composition is. It enters into this object, and obviously, if this object has a lot of hydrogen, oxygen, nitrogen on the top layers, and the space debris is made of rocks, minerals, iron, and nickel, what's going to happen is that material is going to fall inwards and continue falling inwards, and along its path, it's going to do quite a few things. It's going to rub against the atmosphere. When it hits it, it's going to explode, so it's going to send a lot of shrapnel out into it, which breaks it up into tiny, tiny bits. And then you have the fact that it's going to be really hot, so it's going to melt the material. So, okay, you have breaking up, you have melting. In some cases, you have ionization from the heat of the impact, which means it's going to break up what other molecular compounds were or hit the surface of the star. It's going to break up the molecular compounds into ionized matter. That's why a lot of meteors, when they enter in, are so bright, and they're ionizing. All the materials being vaporized and then ionized. That's how much energy it's releasing. So you have it's breaking up, it's melting, it's ionizing. But as it does that, obviously it's going to combine then again with new compounds. So it's going to mix back up into this atmosphere, given whatever material it can mix up with. And as it falls toward the center, it's going to mix in specific proportions, and depending on how evolved this object is, will determine its location on the interior of the forming planet. And the reason why I say this is because we have iron in the surface, obviously, we mine for it. But the majority of the iron and nickel on the Earth do not exist on the surface. The majority of the iron and nickel the Earth is comprised of is in the center. So how exactly did the Earth get surface iron in the form of chemical compounds, which are the ores that I reviewed previously? Well, exactly that. When the Earth was a young gas giant star, it was collecting material from interstellar space, which then fell to the surface, mixing and matching and just doing a whole bunch of crazy all over the surface. But given if Jupiter was a lot younger, this portion of the core wasn't formed yet. This was still hot and diffuse, so it might have stretched out here somewhere, which would mean whatever iron formed would have deposited right there. And And if it was a really young star, like a red dwarf, or even younger like the sun, I think the sun would be a bit too young for this process to really have any effect because it can ionize all the incoming material. But if it's really young like a red dwarf and it's forming its iron nickel core, what could happen is that you could have material entering in, depositing all the way to the center. So you could literally have, okay, I'm going to make this ball a little bit bigger. Imagine this is the solid iron nickel ball, okay? It's a crystalline ball. You could have random material from another star depositing somewhere like right here before these outer layers are forming. So you could have a random bit of metal which does not belong just sticking out, just randomly like that. But also you have to keep in mind that there is a core mantle boundary as well. It isn't cut and dry. It isn't a single solid line, so I guess it's like a really wavy line. Now, given the majority of it is almost perfectly spherical, you do have a boundary where everything is like mixed up in here, and there's not really a lot of cohesion. There isn't really a clear-cut boundary between the mantle and the core when you zoom in on it. Similar to like a cloud. You have a cloud, obviously you see in the sky, and you can say, oh, there's the edge of the cloud. But if you zoom in on that edge, you make it bigger, you'll notice there really isn't a clear-cut defining boundary of the cloud. So you have that too. A lot of material is still mixing in there as well. But I think that really sums up this talk. If you have any questions or comments, please post them below.